Good morning.
Good morning, Rob.
Hey, I just want to do a quick intro. I'm Robert Wilson. I'm Vice President of Sales for ScaleFlux. Joining me today is Eric Pike, our Vice President of Business Development.
Hello, everyone. As Rob pointed out, Eric Pike here, and we're going to have a little bit of fun today with you and talk a little bit about some ScaleFlux SSDs and give you a little bit of an update.
ExSqueeze me, Eric?
Exactly right.
All right, buddy.
All right.
Let's get started. Perfect. What is it and why does it matter? Let's start with the second item first. Why does it matter? So today we're going to be talking about compression, how we make compression different, where we put compression that's different, how we sell a drive that's different, how we're smarter than the other drives, which is different. And Eric's going to tell you the rest.
Perfect.
Okay. Beautiful. Beautiful.
All right. So, we'll start off with the second half, as Rob said, and a little bit about why does it matter, right? And this is a study. There's a lot of studies out there. People have been publishing all sorts of different studies about this stuff. But the key message here, of course, is the amount of data that's being generated, that we're generating every day, just keeps exploding. Pandemic caused things to jump up significantly. So if you just take this particular study, came from IDC, talked about the global data sphere, and just drilling in on 21 to 25, right? About 100 zettabytes of new data is going to be produced. While during that same time period, the industry is going to add about 8 zettabytes of new storage. So 100 zettabytes of data, but only 8 zettabytes of storage, meaning, that a ton of this data is transient. It's, not necessarily needed. But we also know from all of our discussions, and we talk about this, in a lot of different reports, that data is valuable. Right? How do I get more? How can I extend that 8 zettabytes so I don't have to throw, 90% of my data away? How do I get a little bit more out of it? And compression is one of the keys to that story. And so we'll spend a little bit of time on that.
It would seem we need some new technologies to make up that deficit. Absolutely.
Precisely.
Yeah. Perfect. So compression use today. Well, I'm going to talk a little bit about this. Basically, we've got 4 different areas that line up on our left-hand side, or excuse me, our right-hand side. We got DRAM, SSDs, HDDs, and tape. And you can look, most of the compression now is being applied to archival data, where it's frozen, or let's not use the term glacial, right? Because the ability to compress that data and store it is usually mitigated by the amount of storage capacity you have available in any of your different data centers. Whereas in DRAM and SSDs today, since that data is hot or warm, there's absolutely no compression happening on it. If there is, it's going to be host-based compression, which we're going to talk about a little bit today.
That's exactly right. That's exactly right. And just to kind of bring this into one of our real-world experiences, right? Most often today, when the average consumer is using compression, they use a zip file, right? They zip their data. And anybody who's zipped a file, you only do it when you have to, right? You don't want to be zipping files and constantly managing, data from it, because it takes a long time. So, the only 2 reasons you zip files is you zip it so you can free up more space and just put it away, or you do it because you have to, because the file has to be small enough so you can send it through some email server or something.
Exactly.
But
exactly.
As you pointed out, right, that's really the only use case for compression today. Now, as we just mentioned earlier, the global data sphere is much bigger than what the tools we have today. And the truth of the matter is that even though, the most common use of compression today is there's value to using compression in these other tiers, right? If I can, extend and get more out of my tools and my capabilities at these other tiers, then I can actually create more value and get more value from that data while it's still warm.
Right.
Right. So the concept of compression only being used in archival, and we'll talk a little bit about that, is more about the tools and the resources available to us. And that's one of the reasons why you see it there today. And again, this is where ScaleFlux, we're going to come in and talk about how you can move up this, data pyramid and leverage compression in the other domains.
And I can imagine we're going to be talking about it without the latency of running zip files.
Yes.
Okay. Because I'm not a technologist, but I know people that are, and they don't even zip files anymore.
This is true. This is true.
Great.
All right.
Okay, a little bit about compression. So there's two types of compression, as you know, Eric. There's lossless and then there's lossy. All right. And lossless is those files that are really important to me, especially as a consumer, right? It's like my medical files.
Yes.
Let's get another example. How about my credit card statements or my bank account?
Your credit card statements, you may want to be lossy, but you're
until they find out that it's lossy, right? On the other side, if I'm doing a TikTok, I really don't care if that thing exists past 24 hours typically, because I'm getting older now and it's kind of embarrassing. But if somebody wants to compress those files and make them lossy, all that much better.
You're getting hard of hearing too, Rob. So I'm pretty sure that the amount of loss that you can tolerate in an audio file, it doesn't matter that some of the data is thrown out during that compression.
Exactly. So we've got our two types of compression. Now, which one do we focus on here at ScaleFlux?
Yeah, we're going to focus on the lossless, because we're talking about, remember that data pyramid, we're talking about the hot data, right? The valuable data. And so during that time period, right, and mission critical files that your company is working on, you really want to make sure you don't lose any of the data.
Okay.
The other kind of two categories of compression, again, at a very high level, is file versus block. And file is the idea, again, going back to our zip file example, you take the entire file or the entire object or whatever it is you've got, and you compress it all at once. So you're looking across the entire spectrum.
Okay.
Whereas block is looking at it at a piece at a time. And, if I want to draw a little bit of an analogy, think about it like a book, right? In the case of file compression, you take the entire book and you're looking for all of the ability to compress across the entire book all at once.
Okay.
It takes time. Right. But, and you get to find lots of patterns because you get to match across different pages and all sorts of stuff. Block would be the idea of taking one page at a time out of a book, compressing that one page, then compressing the next page, compressing them one at a time.
Okay.
So it might sound like file's easier to implement because I just grab the whole thing and I do it at once, whereas block's done in chunks. But if you flip this around and go back to our data pyramid and talk about the hot data, well, in the case of file compression, if I wanted to make a change of one page, one word on one page in the book, I got to take the entire book,
open it,
decompress the whole darn thing so I can make one change on one page, and then I compress all of it. A lot of waste, a lot of overhead, right? Whereas in the case of block compression, if I wanted to make that one, I just go to that page, decompress just that page, make the edits, compress it back up, and the rest of it, I don't want to affect the rest of it. So block compression works really well with hot data. And so that's why in our technology with SSDs, right, we're focusing in on lossless compression, mission critical data, and block level compression. And we'll go into a little more.
And again, this is on the SSD itself.
Precisely. That's the uniqueness. So I'll take this one, Rob. Lossless data compression. This gets into a little bit of the details around how it works. But it's a very simple idea from the point of view that you're looking for patterns. And when you find those patterns, you replace them with a pointer. Right. And so, and by removing those patterns, the data becomes smaller. The data set becomes smaller. Again, simple concept, but when you think about this in the grand scale of doing this in a server or in an application or a database that you're running, it becomes a little more complex, right? And it's not trivial from the point of view that finding those matches all at once and working through that stuff, and then the result is that matches can be different sizes. So all of this stuff results in data that's different shapes and sizes, and has to look different, but you want to be able to maintain the index because you want to be able to go back and see all that data when you want to. It's kind of like a game of Tetris if you think about it, right?
Right.
You get all these different block sizes. You want to pack them all in together and get the small. The difference with Tetris, of course, is every time you complete a line, it goes away, right? And you kind of don't worry about it. Well, in our case, none of it goes away, right? We retain all this data. So you've got all these blocks you're mixing and matching that are different shapes and sizes, and you got to retain all of them and be able to know where every piece of data is. The result is, to do block level compression, lossless compression, it takes resources. It takes quite a few resources. And we're going to go into a little bit of a discussion of, today, what do those resources look like in a system?
Let me ask you a question. So you're talking about system resources. If I were to do this today without technology like scale fluxes, where would this be happening?
It happens in the host. That's right.
Okay.
It happens as part. And in fact, most software programs have an option where you can turn on compression, right, and utilize it in those systems. So it's done in that same environment where you're actually trying to run your application.
Okay. Got it.
Which
Got it.
leads to the predicament, the challenge, right, for customers. And that predicament is the speed versus size trade-off, right? The more I compress my data, the smaller the footprint, the more money I can save, so on and so forth, right? On the other hand, to compress the data more, it takes more resources. And so what you see on the left-hand side on this graph here is a couple of different examples. This is cited from a nice company out there that decided to rename themselves Meta. They did a study and it kind of looked at exactly what we're talking about here, which is here's a bunch of different compression algorithms. These compression algorithms are the ones that are used in the host, just like you asked about. And the bars in behind show the performance. And so obviously, there's options from really fast to really slow. And then the blue line that's shown in behind it talks about how, the slower you get, the more compressible the data is.
Okay.
So, you're stuck with this dilemma. If I want more performance, I have to give up on the compressibility versus if I want more compressibility, I got to give up on performance.
So it's another one of these conundrums. So you flip the switch in the application.
Yep.
You're hoping to get more performance because your data set size is smaller. But in actuality, the act of this compression happening on that host is taking up those valuable resources that you need to run the application in the first place.
That's exactly right. That's exactly
Total
right.
conundrum.
And so the trade-off, of course, for the system designers is, well, I don't want to give up that performance, right? So the option is I got to add more, right? I add more processing cores, or more DRAM, more system level resource to make up for it. And we'll go into a little bit more complexity. That's right.
More money.
So, beginning on the left-hand side, let's just talk about sort of the compression capability. And very simply, what this chart is showing is you start off with a certain data set, and how much did you compress? And we're comparing those same standards that we just talked about on the previous one to the scale flux option. Simple statement here is that scale flux compresses the data as good as any of the best of those, right? So you're not giving up any of that compressibility, that blue line, at all with scale flux, right? On the other hand, if you go over to the right-hand side, we picked those two bookends. So we picked the LZ4, which was the fastest. It was the fastest. And then we picked the GZIP, which was one of the most compressible versions on that previous.
Right.
Slide. And so on the right-hand side, what you see here is, hey, okay, we want to compare one scale flux SSD to the throughput on those. And the result is you'd have to add about 12 cores to LZ4, right, to get the same level of performance of one scale flux SSD. And you can see on the left-hand side, to use LZ4, 12 cores might not sound like much. It's basically one processor, right? But you're giving up compressibility. Remember, for those high-performance solutions, you got to give up some compressibility. On the other hand, if you don't want to give up any compressibility, you want GZIP, right? You can see GZIP matches the compressibility on the left-hand side.
Right.
Now you got to go get yourself 170 processor cores, which I think if I do the math, that's basically an entire rack of processor cores dedicated to compressibility of the data, just to match one scale flux SSD.
On GZIP. So that was Intel wanting their procs back. Am I correct?
Or enjoying the fact that you're going to buy more.
Got it.
That could be the case.
So that was either accounts receivable or accounts payable at Intel.
That's right.
Thanks,
That's right,
Eric.
Rob.
Well done.
All right. So again, the simple message here is you want the maximum space, and you don't want to be giving up those resources. Plug a scale flux SSD inside, and that's the magic.
Beautiful. Go ahead.
Yeah. So, now we're going to talk a little bit about the ease of use of these devices. So a standard, SSD that you buy out there today, an NVMe SSD we all have this trade-off. Everybody who's familiar with SSDs understands the idea that I can use this term over provisioning.
Mhm.
I basically give up some space, which ends up being cost, and I can get more performance. And so there's this dial that any SSD out there offers you.
Is that the 3.2 between 4 terabytes? We're always talking about
That's
that.
correct. 3.2 versus 3.84.
Right,
Exactly
right.
right. Now, when you overlay that with what ScaleFlex offers with compressibility, it's basically blowing that up, right? You take that compressibility, and now, we do have this, again, similar technology trade-off, but it's on a completely different scale. It's unfair. We've changed the scale. So now you can get accelerated performance and endurance, right? Get all of that goodness at a level that's beyond what you can get out of any NVMe SSD.
All right.
But also, you can dial, all the way over the right and get extended capacity. You can get more than the capacity that the drive you purchased.
So I'm no longer just playing in that little space of over provisioning.
That's right.
I've gone into extended capacity world. Is there another drive out there that'll extend capacity?
Not that we're aware of. Not that we're aware of.
Legally?
That's right. So, we put a little demo together here, Rob, to kind of show just how easy this is. And, this is, for those of us who like command lines and interfaces like that, this is kind of fun to take a look at here. So I'm going to run a little bit of a demo behind the scenes here. This should take just a few seconds. Again, what we've done behind the scenes here is we've plugged one of our drives into a box. That's it. Nothing else is done. There's no other secret sauce at this point. We're literally just plugged one of our drives inside of a box. So the very first thing you'll see here is, we run a NVMe list, and we basically look at what is that drive. And what you see on the information here is this is a CSD 3000, and it's a 3.84 terabyte drive. So at this point, we've got 3.84 terabyte drive plugged into the system, ready to go.
Okay.
Ready to go. Customer could start writing data to this drive right now. Now, this is the default setting as it was shipped. And so this is the, again, the standard capacity. So if you were on that performance capacity curve, this would be on the left-hand side, right? Any compression of the data would result in storing less data on the drive and therefore unleashing more endurance and more performance. Done. You had to do nothing else. Right now, that drive's ready to go. The rest of this demo is going to talk a little bit about what about the extended capacity, right? Because people are like, as you said, there's no drives out there that do this. So let's explain a little bit about what it takes to extend the capacity of the drive. So now we've taken the same drive, plugged into the system. The very first thing we had to do was go in and we had to basically clear out the namespace. We use the namespaces to format the capacity. So the first thing you do is delete the namespace. And then the next step is you go in, we looked at the drive. So this just confirms that the namespace is gone, right? Now there's no capacity allocated. Done. Next step, we set up the new namespace. We create the new namespace. These are the parameters associated with the new namespace. In this particular case, we were setting it up to be an 8 terabyte drive. And you're done. At this stage right now, after this one command right here, you delete the namespace, you create the namespace, you're done. You now have a 7.68 terabyte drive ready to go in your application.
Wait a second. Now, were those standard NVMe commands?
Those were completely standard NVMe commands.
Was there anything like off package, off base?
Nope.
Did we have to go off the reservation here at all?
No, we did not.
Okay, so we're still, there's nothing crazy happening.
And anybody could, anybody who works with namespaces in their environments, right, they run these batch commands. They could run this as a batch command on the install.
Okay.
Everything's fine. It uses standard NVMe commands and set up. And at that point, you now have an 8 terabyte drive ready to go.
So you're saying I can do this at rack level
That's
deployment
correct.
as opposed to host level deployment?
That is exactly right.
Okay.
Now, we did continue the demo on here just for one purpose, just to show people kind of what it looks like when you use compressible data. So we generated a file. We generated a 1 gigabyte file. You'll see this here. We ran a little bit of a command to generate a 1 gigabyte file. And then we wrote that 1 gigabyte file to the drive. And what you see here is this particular file was 2-to-1 compressible. And just to show you, 1 gigabyte file written to the drive resulted in 527 megabytes written to the drive, literally 2-to-1 compressible, just demonstrating what happens when you write data, compressible data to the drive. And again, you didn't have to do anything special here. You just, the drive is doing all of the compression capability. You don't have to manage the compression settings. You don't have to do any setup. The
Right.
drive automatically analyzes the data coming into it and compresses the data to the maximum capability that the drive is, able to do.
Excellent.
That's it.
That was super simple. Even I get that.
That was it. That was it. All right.
Beautiful.
We might have a few questions, I think, that might have come in.
Let's see what we have here. Oh, here's one. This is a great one. We get this question all the time, Eric. How do you know if your data is compressible using a scale flux SSD? Great question.
Yeah, it is. It is. And in order to help our customers out with that, we've actually got a tool that they can download and run. It's they can run it in their environment without an SSD. They can check it out themselves. That will run the compression algorithms that we run on the SSD. That they can run on their own data and see how compressible it is.
Great. Marketing sending another one. Here we go. How does compression actually enable better performance? Because we went back to the conundrum slide. Wait a second.
Yeah.
Sounds like a little too much secret sauce happening.
So the previous webinar that I did with Pete actually dug into this a little bit further. Right?
Okay.
We spent that webinar on this, but just a very simple summary. And again, I recommend those of you who want to learn more, go watch that webinar. Very simple summary for SSDs is any SSD as it gets full, it slows down a little bit. That's just inherent in the nature of the SSD.
Okay.
Obviously, when we compress data, we're going to slow down the rate of it getting full. In fact, in some cases, the drive never gets full.
Right.
And if it never gets full, you never experience that slowdown, and therefore you get significantly more performance out of your SSD.
Okay. Excellent. So we have another one. Oh, here's a good one. Where can I learn more about how to manage the compressibility of the FIO test data setup?
Yeah. So again, as Rob and I have talked about here, this idea of using compression is a little bit new to people. And so, people want to run test setups and want to sort of figure out different compressible data sets. You can use the FIO tool. The FIO tool itself has the ability to configure the compressibility of the data that it generates, because it's supposed to generate random data, but you can actually manipulate how compressible the data is. We have instructions for that on our user guide and user information. So again, reach out to us. We'll provide you that information. It's on the standard FIO tool that you can run that capability and generate data that has different compression levels so you can evaluate your environment.
So people can kind of pre-stage their application/use case
Yes.
to see what their compressibility will be even before they talk to
That's right.
a scale flux sales rep?
Now, we always recommend that customers try to use the closest to their live data, to their actual data, to their real environment, because they're going to see the real result. But we know FIO is often used, and so you can use FIO to generate that data.
Excellent. Excellent. See if there's another one here. Here's a great one. So someone saw we're releasing a new drive, Eric. What's improved?
You want to take this one, Rob?
Eric, I think I do. This is a good one. So just about everything is the answer, except for our performance. Our performance came in our last drive about equal to where we are today, with the exception of the fact that we're now running Gen 4 PCIe. So we've got some distinct advantages on the new drive versus Gen 3. But today, as it stands, this drive has 0 host-based resources take up. It's got all NVMe commands, as we saw. We're not taking anything away from the host as far as driver concerns go. We were previously driver-based. And, at the end of the day, this is plug and play. So everything that the audience has seen so far is simply an NVMe drive swap versus putting in a computational storage device, as we called it before. So this is truly an NVMe drive. It's not a computational storage device. It's not limited in any way, shape, and form for its ability to transcend different applications. And it's got absolutely fantastic performance, especially when compression is on.
That's right. Yeah, and just to clarify, I think the compression capability of the drive is exactly the same as the previous generation, right? The
Bingo.
performance, of course, with Gen 3 versus Gen 4 is twice the performance. So while the data is equally as compressible, the output of the drive is twice as good as the previous one.
Thank you. Thank you.
Yep.
What do we got? Any more? Let's see. Do you also offer SATA SSDs? Or excuse me, do you also offer SSDs with a SATA interface? Good question.
Yeah, today we don't. We're focused on the NVMe standard in terms of providing that solution. We're obviously interested in continuing to move forward and match that capability of the system performance, which putting it on the PCIe bus gives us that tremendous
The zing.
performance advantage there,
Yep.
that solution.
Great. What do we have here? Oh, here's another one. Are your drives still limited to Linux, or do you support Microsoft and VMware environments? This is probably from our friends at Azure.
Yeah, that's true. That very much. Maybe not the VMware part of it, but
Right.
yeah, the simple answer is we support all the environments that NVMe is capable of. Now that we're NVMe standard, as Rob outlined with our third generation device, anywhere you can use an NVMe drive, ScaleFlex drives can be deployed. So no, we're not limited to Linux.
Game changer.
Do we have any more questions? Don't think so.
A second one. Doesn't look like we have any.
You want to wrap us up, Rob?
Absolutely, Eric. Eric, thank you very much for today.
Yeah.
That was very informative, even for me. Okay, I could actually follow along, so thank you. And thank you, audience, for participating today in our series of 3 webinars. Whoops, we got one more.
Oh.
Can you talk a little bit about the cost of our drives? Eric, take it away.
Yeah. So
I want to handle that because as the sales VP, we always make it work. So I'll let you take this.
So the base device technology is competitive with the NVMe drives that you have in the market. So from a core capability point of view and from a core cost point of view, it's we have equivalent costs to the rest. Where the cost dynamic completely changes, obviously, is when you think about the cost per gig based on the compressibility of the data. Right? If I have 2-to-1 compressible data, I've effectively halved the cost per gigabyte of the storage environment that you're in. So and from a performance point of view, right now with compressible data, we get unmatched performance, right? We talked again a little bit about this in the previous webinar. So if you're performance or capacity, constrained, going back to that little diagram that we put on there, you're going to get cost per gigabyte or cost per throughput per IOP that's unmatched relative to the rest of the industry.
So we've got twice the performance of a standard NVMe drive, Gen 4 to Gen 4. We've got twice the capacity of a 4 terabyte NVMe drive, which basically halves the cost.
Yeah.
I love those questions.
We have a couple more.
Great. This is from Tony. He asked the question, do we need more RAM to support this new SSD?
Yeah, so system level RAM, none at all, right? Again, that's part of what Rob referred to is that from a moving away from the host-based driver on our prior generation to a standard NVMe-based drive, there's no system level RAM. As far as RAM inside the device, we do use RAM inside of the device as part of the solution, as every SSD does.
Right.
And the answer in terms of do we need more RAM, it kind of depends on which capacity configuration. But there is a little bit more RAM inside of the device. That is true. But again, going back to the performance versus cost examples, anybody who understands the dynamics of an SSD can understand that that's a fraction of the total cost of an SSD.
So we're apples to apples versus the driver-based product, which was apples to oranges as far as the DRAM consumption is concerned.
Yep.
Great. These are great questions. Well, let me try this wrapping up again, because every time I wrap up, we get more questions.
That's perfect.
Okay, super. So thank you again, Eric. Thank you, marketing, for putting this on. Thank you, Accelerate. You guys have been phenomenal as far as our webinar series goes. If there's anybody out there that's looking for a partner to help us do this, then that helps us do this, there's no better than Accelerate. So let me do one more. Oh my gosh, see, Tony got me. He said, thanks. What about CPU overhead? This is beautiful. Thanks, Tony.
Yeah, and short answer is, Tony, as we showed on the earlier, 0, right? There's no CPU overhead. The compression is done transparently inside the drive. So again, you plug and play this with any other NVMe drive. Therefore, there's no CPU or host resources required to enable this capability.
Right. And we did that by building our own SoC. So I think that's the differential here. We're actually building our own processor on the drive itself.
All right.
Okay, guys. Thank
Awesome.
you very much. Hey, you guys, as you leave, make sure to scan the QR code for a free POC. And we'll see you at the Flash Memory Summit, August 2nd. Please stop by and visit us. We love to see our customers. We love to see our end users, and we love to see our competitors every day. So please stop by.
Thank you.
Thank you. Bye-bye.
Bye-bye.